Okay, so yeah, this is part one of two talks. I'm going to talk about high altitude water and cloud satellite mission, and I'm going to focus primarily on the overall mission, the objectives, and a little bit of the science. And the second talk is going to be given by Landon Rieger. He's going to focus primarily on some synergy aspects of the mission. So I guess I wanted to point out from the beginning, like I maybe met a few people here, but I don't know most of the people in the room. So my name is Jeffery Langille, and I'm at the University of New Brunswick. I'm a research scientist there, working with William Ward at UNB. But I did my postdoc with Adam and Doug in Saskatchewan, and working on one of the instruments that's part of HAWK. Adam is the PI of ALTIUS, the aerosol imager instrument. And Doug is the PI of the SHOW instrument, the Spatial Heterodyne Observations of Water instrument. We also have a third instrument called TICFIRE. It's a long-wave radiometer imager. And that one, the PI is Jean-Pierre Blanchet. And then there's the three instrument scientists, so myself, Landon, and Jan Blanchard. Okay, so I want to put this in the context of the Atmosphere Observing System, which is part of NASA's Earth System Observatory. So the last decadal survey, it was identified that, I guess it was separated out in terms of aerosol and then cloud convection and precipitation. They were identified as being areas of importance to study. So they've identified lots of questions that needed to be answered with those. And the Atmosphere Observing System is one component of the Earth System Observatory designed to specifically answer questions related to aerosol, cloud, convection, and precipitation. And then there was a 2-year intensive mission that lasted from, I guess, 2020 until 2022 to formulate a new $1.6 billion satellite constellation, and this is shown on the slide here. There's contributions from JAXA, Canada, and then there's also CNES has some contribution there. And there's an inclined orbit and a polar orbit, and that looks like it's baked in that will happen now. But there's still some conversations about what types of radars are there. So radars, radiometers, and the HSRL LiDAR that's listed on there is no longer going to fly. It'll be a backscatter LiDAR in that polar orbit. So back in October of 2022, we got the official announcement from the Canadian government that they were going to fully fund the HAWK mission, which was great news for Canada. It's the first atmospheric science mission since ACE, so that's a really significant thing for Canada to contribute to. Somewhere upward of $200 million formally committed by the Canadian government. And it really is a pan-Canadian mission, so there's, I think, 13 institutions involved now. They're not all listed on here. These are the ones that were listed as part of a CFI proposal put forward to support the project. I do want to point out the involvement of U of T and McGill specifically, because U of T is taking the lead role in the suborbital component. It's primarily led by Kaylee Walker. And Yi Huang from McGill is playing a lead role in developing a science case around the mission. Okay, so there's three instruments. TICFIRE is a nadir pointing imaging radiometer looking down, and it will fly on the polar AOS satellite. And then we have SHOW and ALTIUS both looking at the limb, and they'll fly on the satellite, what we're calling HawkSat. And ALTIUS is going to retrieve aerosol extinction, aerosol particle size, cloud top height, and SHOW will do measurements of water vapor. And this is specifically to target the UTLS region. And then you have TICFIRE looking down at the nadir direction, doing retrievals of ice cloud microphysical properties. Also, they'll get some water vapor information and temperature as well. But it's sort of coarse resolution measurements. But they are looking in the two-dimensional, so that's kind of interesting to look at too. Okay, so it's probably no surprise to people in this room that the UTLS aerosol, water vapor, and cloud play an important role in climate. It's come up multiple times in various talks already. But it is important to point out that there's really clear knowledge gaps. For example, aerosol measurements in UTLS are complicated by poorly constrained microphysics, especially in the presence of thin cloud. And in the case of water vapor, and this is talked about by a few people already as well, that there's very clear differences between different measurements that are made by different instruments, especially in the UTLS, and it's likely associated with inadequate spatial sampling, especially near the tropopause. And then you also have aerosol and cloud interactions, which are really interesting and important. So thin cirrus have important interactions with aerosol, but this is really difficult to measure. So that's something that we're going to look at. And aerosols influence the seeding, particle growth, and then water vapor sort of links them all together, right? So it influences the growth of the particles as well, and sort of modulates the size of the ice crystals. So water vapor is playing a really important role as well. Okay, so Hawk on AOS. So AOS primarily is looking at things below the tropopause. Almost all of their interest lies below the tropopause. So Hawk on AOS is quite important because we're providing an enhanced set of measurements up into the UTLS. And we have a really high sensitivity to aerosol and thin cloud and low water concentrations. And that's quite important in the UTLS region. And it'll help AOS extend to these higher altitudes and lower loading conditions. We also are providing really high spatial resolution measurements. So both ALI and SHOW are targeting less than 500 meter vertical sampling and 200 kilometer along track resolution. Now SHOW is sampling at 2 seconds, so we're getting 15 kilometer spatial sampling. We'll see what we can pull out of that, maybe using tomography, but just doing the single profiles, it's around 200 kilometers. And then TICFire provides this nadir view with the far infrared imagery, so providing cloud particle size information. There's also really strong synergy between the Hawk instruments, providing good information on cloud and aerosol interaction at high altitudes and cold regions, which is important for the Canadian perspective. And this does respond to decadal survey questions that are not directly targeted by the AOS baseline measurements, so it really is an enhancing component of the overall mission. And we get this polar orbit that will give us the global coverage and hopefully contribute to some long-term climate records. So I'll talk about all three instruments really briefly. The aerosol limb imager is a 2D multi-spectral imager. Looking out at the limb, the footprint of the limb is around 45 kilometer in the altitude, and then about 200 kilometer in the cross track. And that'll be sampled down to 10 samples, so about 20 kilometer cross-track resolution. And in the figure here, let's see if I can. So this is showing all of the bands that ALI will target. So as you move along the track, it's showing these different bands. And it's a dual polarization instrument, so this is the cycling between the polarizations. So that'll provide some ability to do cloud discrimination, which is quite interesting. And the wavelength region is between 610 and 1560 nanometers. So this is just a summary of the ALI data products and an example retrieval that Landon put together for the presentation. So aerosol extinction, effective radius, and cloud top altitude are the primary products. Really high vertical resolution and really good along track and cross track sampling. And then for the water vapor measurement, the instrument is the Spatial Heterodyne Observations of Water instrument. And this is the SHS is configured in the limb viewing configuration, to look at limb scattered radiance in a vibrational band of water, sort of near 1363 nanometers. This is a narrow spectral region, but you get a really high spectral resolution within this region, combined with a large throughput, and you don't have to scan the instrument. So that's quite important because we can get 2 second sampling along the orbit track, so really rapid sampling. You get these vertically resolved images of the limb radiance, and then you invert them to get the water vapor profile. And if you stack them along the orbit curtain, you get this nice curtain of water vapor measurements. And the technique allows for this dense sampling of the water vapor distribution. In summary for SHOW, yes, it's looking at limb scattered radiance in a vibrational band of water, really high sensitivity to low water concentrations, and then stacked to provide the dense sampling. This 0.5 kilometer resolution near the tropopause is really important to resolve a lot of the filamentary structures you see near the tropopause that don't get resolved by current state-of-the-art instruments. And this goal of 50 kilometer horizontal resolution would only be achieved using tomography. Without tomography, we're looking around 200 kilometers. And then things are slightly reduced up in the stratosphere, mostly because of signal-to-noise ratio issues. But this is still quite good resolutions in the stratosphere as well. And then finally, with tick fire, looking in the nadir, two-dimensional nadir imaging in the thermal and far infrared. This is a really interesting instrument. It's going from 0 to 80 microns, and it's looking at eight different bands. And there's all kinds of different sensitivities in these bands to particle size and other cloud properties, cloud optical depth. This is just an example of the two-dimensional image in a few of these bands. And there really is a wealth of information you can pull out of that. I mean, there's obviously the broadband radiances, which are quite important for the NASA mission. It's essentially fixing the long wave radiation, especially near the pole, which is not well understood or well known. You also get cloud radiative effects, cloud top, ice water path, cloud optical depth, ice crystal effective diameter, cloud fraction, so really a nice wealth of information. So sort of tying it all together, we get this really rich perspective of aerosol, water, and cloud interaction near the tropopause. And this will be pretty critical to understand things like thin cirrus formation and distribution globally. So this is really what we're hoping to target with the combination of these three instruments. But alone, the instruments have pretty significant contributions as well. Like if you look at just the aerosol and cloud perspective, there's these cases where you can get good alignment between Calypso and OPS, where they basically go through the same orbit track. And you can combine them together to look at the interaction between the aerosol and the cloud. And this is following the Reikoke eruption, maybe a couple months after. I guess this one's September. So there's this background aerosol profile associated with, a background elevated aerosol profile associated with this eruption. And, there's a really clear interaction between the aerosol, water, and cloud, especially, it's really prominent near the break here, the tropopause break, and then also in the polar region. And, the link between that is coupled to the weather really clearly. And I'll show a slide in a few slides here, what that looks like. And I guess, so with aerosols, being able to look at the aerosols globally and getting that thin aerosol stuff, it's a substantial fraction of the total loading, and it's an important contributor to the climate. And with water vapor, this came up on a few talks, so I don't have to go through this in great detail, but the mechanisms by which water makes its way into the lowermost stratosphere aren't well understood. I mean, people know what they are, but it's a question of which ones dominate and which ones are the most important. So things like convective moistening, it's clear that it happens, but how dominant is it globally, and what's its influence longer term on water vapor trends in the lowermost stratosphere? It's an interesting problem that still needs to be resolved. Yeah, and this example on the slide here is just an example where MLS also did an overpass pretty close to a Calypso and OMS orbit. And you can see there's really good correlation between the aerosol and cloud here, but then if you look down here at the MLS measurement, you can almost see that MLS is starting to see something just above the tropopause that is almost kind of correlated with the aerosol and cloud, which is really quite interesting, but it's still not good enough vertical resolution to resolve it. So it's important to get that higher vertical resolution. And this is an example of what you can get with an instrument like SHOW. This paper was published in JGR Atmospheres by members of our team from Yi Huang's group, where they looked at a simulated convective moistening event where there was this moist plume generated above the tropopause in the advent of the convective moistening event. And then if you look at using these sort of spatial averaging kernels for the MLS instrument and AIRS, you just don't resolve the plume. But if you do have the spatial resolution that we hope to get with SHOW, it does pull out that filamentary structure associated with the plume. So quite an interesting result too. And then finally, I wanted to reiterate the sort of link between the weather and the variability that's going on here. This is something we're working on trying to understand and put it in the context of the meteorological perspective, so it isn't completely understood just yet. But this is a case that Jean-Pierre Blanchet is helping us sort of flesh out. But you can really link the interactions between the cloud and the aerosol to these weather features. And that's really quite interesting to think about how they're coupled together and near the tropopause. And this is something that the AOS baseline instruments wouldn't be able to look at alone without the Hawk instrument. So a really interesting contribution. So as a summary, Hawk is a fully funded Canadian mission contributed to NASA's AOS. There's 3 instruments, SHOW, ALI on HawkSat, TICFIRE on the AOS polar satellite. We're combining LIM observations of UTLS, water vapor, and aerosol with nadir observation of long wave radiances, microphysical properties of cloud, and looking at targeting high altitude and cold regions, getting a good global coverage with the polar orbit, looking to increase our understanding of cloud aerosol feedbacks that influence frequency of high cloud and thin cirrus cloud, further studies of aerosol cloud and water vapor interaction to improve model fidelity, hopefully, and then investigating cloud interaction with aerosol, water vapor, and radiation in the Arctic. So putting in a little bit of a Canadian perspective. And that's it.